again at the current frequency, and this is equal to that. You get 1 here, so that goes to infinity. And it converges down to the unguided mode afterwards. Well, if you do the same thing, eta guided, MN, or eta unguided, for the TM modes, turns out to be the square root 1 minus MC. So the TM modes start with 0 at this point and converges to the unguided. Now, what I'd like to do is go back to the situation when we had two plane waves traveling at an angle with respect to the z-axis. If you remember, we've done that. And we did the plus and minus. The sinusoids are, let's say, going to be doing like this. Let's see if we can do a good job on one of those at least. All right. So this is minus, plus, minus, plus, etc. And the second wave, this is like your pointing vector, or that's your coordinate here. It's called the Z1, wave 1, and Z2 for the wave 2. Again, they are synchronized here, so it's going to be the same thing. It's going to be positive here. So let's see here. That's, I'm going to do that dotted. It's going to be negative here, positive, negative, etc. So it's going to be positive here, again dotted. Because I don't have any colored chalk. So that's one here is negative, positive, negative, positive, etc. And we said negative and positive gives you 0 here. All right. Negative and negative gives you negative there, so that's negative. Positive and positive gives you positive, and so on and so forth. Negative, positive, and you have zeros everywhere on these lines. When negative and positive meet, you get zeros. So we said if we look at this problem, and the problem we're working on of having two conductors, the z coordinate here, in both cases here, these are 0 potential, grounded. The boundary conditions are the same. The media inside is the same. In both cases, we'll assume the same exact material. Then, according to the uniqueness theorem, we should have the same exact solution. So the solution we're seeing here is identical to the solution we're seeing there. Right? Now, as it turned out, that if you look at the wavelength here now, let's look at this was positive. The wavelength here is going to be this distance here. From here to there, that's your wavelength. Right? That's exactly lambda got. What's your number?
5,000.
5. Instead of opening all of them. Not 5.5, 5.7, huh?
5,000.
No, I'm talking about the last quotation.
Oh, yeah. Oh,
I ended up looking at it anyway. So the thing is, that's your lender guide. Meanwhile, this was the lender unguided right there, between one of those positives and one of those positives. That was lender unguided. Okay, lender issue. So if you look at this triangle here, that's a 90-degree angle here. Say that's the angle theta there. Okay. So you can say lambda guide cosine theta is equal to lambda unguided. Right? So that gives you lambda guide or lambda unguided is equal to 1 over cosine theta. And that's certainly greater than 1. And that's exactly what we're seeing here again. That's the same diagram as lambda guided over lambda unguided. Same exact diagram. Same exact equation. From this kind of thing here, although that this is only an unclosed situation, these are actually nothing but parallel planes, right? We did not close them for the other sides. If we close them for other sides, obviously there will be more complications of the picture, but nevertheless the same kind of concept. Same kind of concept that lambda, the guide is greater than lambda unguided. And the ratio between them is related to the angle of your individual waves. And basically these are nothing but the pointing vector of this wave, and this is a pointing vector of the other wave. And if you really think about drawing the rest of the pointing vectors, you'll discover that that's exactly what happens here. That the waves will be bouncing back and forth. See the angle theta there. Right, these two angles are the same. All right? And that's your direction of the pointing vector. S. Uppercase S is the pointing vector. In some other notation, some other books use P, script P, but nevertheless, that's your pointing vector. So your waves are bouncing back and forth. And the pointing vector, as we mentioned before, is just like ray optics. These are the direction of your optical rays if you do ray optics. And that's actually also how we picture what happens inside a waveguide. A fiber, a dielectric waveguide or a fiber optics. All right, is the optical rays bounce back and forth between the boundaries, right? So the angle here of this is determined by that. Now, if you look at this one here, that's M and N. That means your theta is going to be M and N as well. So the different modes are going to be traveling at different angles. So that's one mode. Another mode will be traveling like this. Another mode will be traveling like that. And obviously there will be a lower or a dominant mode, like in situation here, we decided that the TE10 is the dominant mode. Alright, so if you do the TE10, let's do the 10. TE10 mode. That ratio is 1 over the square root of 1 plus F sub C is going to be what? It's let's write it on the side here. Omega sub c mn mu epsilon is equal to the square root of m pi over a squared plus n pi over b squared. All right? So f sub c is going to be normal square root. I'm sorry. F sub c is going to be 1 over 2 pi, and you have 1 over square root of mu epsilon, which is actually C phase unguided. Okay? The square root. And then 1 over the square root of, times the square root of m pi over a squared plus m pi over b squared. So this is going to be, the 1, 0 is going to be pi over a. So you have 1 over 2 phase unguided over 2 a. All right? So if we were to say the X-band waveguide, A is 9 inches. We said before that that's this FC10. That's going to be FC10 is about 6.5 gigahertz. So I put here 6.5 gigahertz divided by my frequency. Say we're operating like 10 gigahertz. Right? You can get the angle of this mode at that particular frequency. Right? That's how you work this one out. Now the thing about multi-mode, we discussed that before. If each mode has its own phase velocity, and it also has its own angle, that means all these modes are not going to arrive at the same time. That's what causes dispersion. We mentioned that a few times now, so you have that already. I'm trying to fill in the bits and pieces that I haven't covered in rectangular guides so we can wrap this up. What else would I... There was one thing, yeah, I wanted to show the TE and the TM modes on the spectrum. Yeah, that was the last time. For the TM modes, if you remember the expression, we had H sub E sub z was in the form of, and we have EX, EY, HX, HY. So that was sine pi, m pi. I'm trying to remember x over a. You can help me out if I have anything wrong here. Sine n pi y over b times e naught plus e to the minus j beta guide z mn. I can't remember which one is sine and cosine. These were sines and cosines. Sine and cosine. Cosine, sine, something like that. The EX will go with the HY, so that will be sine and cosine or the other way around, and this will be cosine and sine or the other way around. it's obvious that if you put m is equal to 0 or n is equal to 0, either one will kill E sub z. So if you go to the tabulation here, mn, and you put 0, 0, 0, 1, 1, 0, next will be 1, 1, etc. All these will yield E sub z is 0. And if your E sub z is 0 and your H sub z is already 0, obviously for the Tm mode H sub z is already 0, then in this case here you have both E sub z and H sub z are zeros, and these are the transverse electromagnetic situation TEM modes, and these don't exist. So this becomes the lowest TM mode that can exist. Based on that, we go on the frequency axis. So the DC here, the 1-0 mode, TE10 mode will be the lowest order mode that will exist. And if we say A is greater than 2B, which we said before is the best situation that we can use, then you have the TE02, the 20 will be the next one. Right after that you get TE01. That will be TE30. TE11 will be right there. And also TM11. So somewhere in here, M and N will be ones. And somewhere in here, maybe 2-1, TE21, you get TM21. Whenever your M and N are not zeros, you get the TMs. Otherwise, you don't see any M or N equal to 0. So obviously, this is the only reason that we have a single mode, the dominant mode. Right? That's a single. Beyond that, you get more than one. So if you go to here, for example, right, this frequency, you can see that you have 1, 2, 3, 4 modes, actually 5 modes, because you have 1, 2, 3, 4 TE modes plus 1 TM mode. So it's obvious that the 1-1 situation, you have both TE and TM. And that means it's neither, right? We have, for this 1-1 mode here, M is equal to 1, N is equal to 1. You have TM solution, and you have TE solution. And remember, we need to worry about the superposition. That means neither TE nor TM. When you superimpose them, you will always have an E sub z and H sub z. Both of them will coexist, right? So TM solutions cannot exist by themselves. They have to always exist in conjunction with TE modes, unless we do something about that, right? Sometimes you would like to operate the guide in a mode other than its default modes. Like we said, for example, the TE10 is the dominant mode. The TE10, if you go back here, that's your y-axis, that's your x-axis. Your electric field was sitting like this, was shrinking down to 0 the other side. That's your TE10 mode. Suppose I'd like to operate in the 20 mode. Let's see the TE20 mode. what will it look like? It will look like this, shrink to 0, and then flip around and do like that. Because what you have now is a distribution of your EY like this. Your EY in this case was doing this. Okay, that's your TE01. So suppose for some reason you'd like to operate in this mode and not in that mode. So what do? So you get your frequency down here, then you get two modes, right? If you operate in this frequency range, so you will, first thing you do is you do your F greater than FC20. That means you get all the TE10 and the TE20. Right? Obviously, you don't have much region to operate here before you get your TE01. So actually, that's your frequency range right there, to be able to get this and that. All right? If you go further here, you get a third mode. Possibly you get, let's say, and possibly, the next would be TE01, right? What does it look like, the TE01? So let's look at the TE01. Your field is going to be like this. You'll have EX, you won't have an EY at all, right? Which will shrink down to 0 on either side. That's EX. Correct? So how do I get this mode to operate while killing these two? So just like having a situation that you have three sources here in one. In your circuit, you have the TE10 source, you have the TE20 source, and you have the TE01 source. So you'd like to operate a short here and short there, and let that survive. So to short this mode, you want to kill E sub y. So what we do is we kill E sub y by shorting these to each other. That kills the TE101, right? You short that, bring that amplitude to 0. This one here, if you would like to put a short here, okay, that obviously will kill that mode, but may give rise to the TE instead of 0102. The 02 looks like this, right? The 02 looks like this. That's your 02. So if you put a short here again, that will kill the TE, but we'll let that happen if you are up there, if you get up there, if you get 02, what is 02? Somewhere near 02. So it's way before the 02, so this may not exist anyway. So it's turned out that if I do that, if I short my guide at this location, I'll be okay, but that means I'm breaking my guide in two guides. So obviously, you don't quite do it this way. What you do is you go inside the guide and along the line here, and occasionally you put some short wire. You don't do it the whole way. You don't do a wall. You don't build a wall. Right? You like to still treat it as a one guide, but you introduce short circuits, occasional short circuits inside the guide along that vertical thing. And you see some of those guides, take them up, look through them, and you'll see like almost like a wall built by wires, right? Between the top and the bottom. These are called mode filters, right? You basically kill the mode by introducing a mode filter like that. And once you kill it in amplitude, you don't expect it to exist the whole distance unless you go through a disturbance that may give rise to it again. So if you go around a bend, or a twist or anything like that, you start to worry about adding the mode filter again. Just like you want to keep it at a minimum. There are some samples of that kind of situation here. This one in particular, in the microwave lab, in one of the enclosures there, we have some of those mode filters that are sitting there. Next time you are in the lab, you ask Kareem to show them to you. Well, let's talk about the midterm again. I still have 5 people that are not here today. Like I said, I'm not too happy about some of the mistakes that I've seen in the solutions, and also the fact that most of your work has been kind of scribbling. Very few that did some neat writing. Smith charts are not labeled, right? You had 3 hours, and I expect 3 hours to be plenty of time for an exam like this that typically is given in an hour and a half, right? So, and I expect also people to go over their solution again and perfect their addition and subtractions. I see some things of that nature. The one thing that I'm going to speak about here is the Thevenin's equivalent problem. So what I was saying, because I was asked if I'm going to curve or not, right? You will take this home and you will perfect your solution and you will submit it again, right? If you had a perfect score in one part, you're going to have to redo that again, unless you're going to rewrite it neat, okay? And otherwise, I would like to see resubmission of that. Now, the Thevenin's equivalent problem. Now, if you notice, in most of my problems, you didn't have any odd numbers for lengths. You know, the length was either lambda by 2 or lambda by 4. So those of you who sat down and did e to the j beta L, was no need for that. It was, you know, if you just pay attention, you will discover that the length is lambda by 2, and right away you know the properties of a lambda by 2 line. Another problem was lambda by 4, and you know the properties of lambda by 4 line. So you didn't have to rederive that part. You could have just written, since it's lambda by 2 line, the input impedance is equal to, right? And the Thevenin situation is, I wanted you to find the Thevenins at this location. What do you do to find the Thevenins at some location? Is you take the load out and you look at the rest of the circle. So that's the rest of the circle. I wish I saw someone doing that and saying, this is your Thevenin's equivalent. So eventually it comes down to an impedance and an open source, V Thevenins and Z Thevenins. V Thevenins would be the impedance seen here, and V Thevenins is the V open circuit that you see here. So you want to solve this problem for your open circuit voltage here. I was surprised to see a few that just ignored the line completely. Or people that added this impedance to that impedance. You know, that line here had a Z0, and this one has a ZS, and I've seen people add these to each other. That's back in the DC low frequency circuits, and even in this case, Z0, as we mentioned several times, is not a real impedance that exists somewhere on the line. It's not a series impedance sitting here. It's a characteristic number for this line. So it doesn't get added like that, right? So that's really what you should be doing. Solve this problem for V open circuit here. Find that voltage. You have 2 choices here. Either you write your equations here, V of Z is equal to you need to find V plus and V minus, or V plus and gamma, whichever way you do it, and eventually put Z is equal to L. Then you find the voltage over there. That takes about 3 lines. You should be able to do that in 3 lines. If you do it in more than 3 lines, then you don't quite understand what you're doing. I've seen people spend about 3 pages, get the right answer, but it tells me right away that there's no good understanding. You know, when you spend 3 pages to find the voltage, there's a big question mark, right? Obviously, when you don't get it in the first place, that's also another question mark. Z Thevenin's, many of you were able to get that, right? Although not all of the class was able to get it right. So that is, once you do that now, the next thing was to find the voltage actually here. Then you do, so that's step 1. Step 2, step 3 is to put them together now. Put ZL here, Z Thevenin's here, V Thevenin's there, and solve a regular circuit now to find the voltage at the load. Right? That's your voltage divider now. Okay. The second issue that I'm telling you about, the things that struck me were very obvious. The Smith chart, the matching problem, was a very critical point here in the solution. Use the Smith chart to design an inductive short circuit shunt stub. Inductive short circuit. All right? We know that there are always more than one solution. All right? And I was looking for the inductive one. All right? Many of you just skipped that word inductive and went on and gave me the wrong solution. So you want to make sure that you did the inductive stub. And guess what? Inductance is the positive J or the negative J? Positive. Positive J impedance. Oh yeah. Okay? Many of you fell into that trap. And inductance gives you positive J impedance, yes, but it could be a negative admittance, negative J admittance. Right? So please be careful with these little things. It's little, but you should open your eyes for these things. Number 2B. Many of you were able to find the length of the line okay, right? And that was good. And then failed to get the known impedance, the unknown impedance. Right? So you already know what the line length is. And you know Z input, how much is ZL? I know most of the problems that we had before is given ZL, find Z input. Now this is the other way around. Given Z input, find ZL. You have 2 choices. The people that got it right got it through the Smith chart. Right? Okay? And if you do it with the Smith chart, fortunately or unfortunately, if you move towards the load or move towards the generator with the same distance, you get the same answer. But you really have to be aware that now, if you start with this impedance, you're moving towards the load to get the right impedance. If you move towards the generator, it means there's lack of understanding. Right? You need to move through the load to get that. But those of you who did with Smith chart, now when you redo it, I want you to do analytical. Right? You see, like I said, I would like to see a perfect performance here. I want everyone to get a 40 out of 40 on the resubmission. Please. Okay? If you get less than 40, if you get 39, I'm not going to give you the curve. I would like to see a 40 out of 40 on the resubmission. I'm telling you about things I'm giving you. This time I'll give you 4 hours. Okay? You get 4 hours this time. I'd like to see a perfect submission. what else? Let me tell you what else. There was one more thing that I wanted to. The bounce diagram, I've seen some careless addition and subtractions. You know, people again scribbling and losing track of the numbers, and obviously you lose, you don't get the right numbers. Most of you, did okay on the bounce diagram in terms of the reflection coefficient, all the details, and then mess it up in keeping good bookkeeping of which wave goes where and which one gets added and which one gets subtracted. Now, the last problem regarding the voltage minimum. Okay, I'm going to show it to you on the Smith chart, and I want you to do it analytically and Smith chart wise. I don't want you to know. So everything that you've done on the Smith chart this time, I would like you to practice doing it analytically as well. So you know your voltage minimum happens right here. Right? On the Smith chart, that's where your voltage minimum happens. So if I go on the line, and here's my signal, is doing that, and I know where the voltage minimum is, right? And there's a load here somewhere. All what I need to do is move from the voltage minimum back towards the load, that distance. If you move that distance from the minimum to the load, right? So you move from the minimum, that distance, towards the load, you should get your unknown impedance. This particular problem has practical application because that's usually how we determine unknown impedances in the laboratory. We'll go on the line, put the unknown impedance, and locate the voltage minimum, and move that distance back, and we are able to identify how much that impedance is.